Before going into more detail in the expressions we have just commented and that we'll be expanding later on, I want to show you a couple of animations that may help you to understand the physical problem we are dealing with. The first one was produced by the University of Granada and will show you the fields created by a Gaussian pulse of current that will be moving along just a wire that has a zigzag on it. It's not a straight wire. So you're going to see the effects of the current as it moves along. The yellow pulse was the current pulse. The other lines you see are the field lines. I'm going to play again the animation, trying to stop at certain points to give you some feeling of what is going on. You see the red pulse in the center here, and this is the current pulse. You just saw that when the current pulse started to come in this way, just a spherical wave was produced. And now, here, the current, when it turns in this point, once again is going to radiate. So now you're going to see how a new spherical wave appears. You see it there. This is just this one. That's the first one. This is the first wavefront that is going along. And you have here the second one. If you look at the yellow color here, that means that the pulse is just losing power. Why? Because it's radiating into space. If we continue, now a new wavefront will be generated. And this is the one, and the previous two have been traveling at the velocity of light. Now the pulse is going to go along this point, and when it reaches the end, we'll have to go back and return. And again, a new wave will be produced. Now you see, in this case, that we have many different waves nested, one inside the other. Have here just a set of waves. And as those waves progress, then you see that they become weaker and weaker. Why? Because they are, as they expand in space, once again they are carrying less power density along with them. And now the pulse will just reach the end, almost exhausted of its power. Here you have 4 snapshots of the same process, and this will help you to understand and follow what we've been talking about. In the first one, we have the 2 wavefronts here. Now a new one will be appearing, it's this one, and see how this becomes larger and larger, and the nested set of wavefronts are being produced. But each one of them, remember, is being produced when the pulse just changes along those points or reaches the end. And this is where the charges are subject to acceleration. So to have those fields, remember, we have to accelerate the charges. This is the second animation I want to show you. You may go to this website and find not only this animation for a charge that is being accelerated, but some different ones. This is just a Wolfram website, and the animation really goes this way. We have at this point a charge, and this charge is going to move along this path at a very high velocity. It's half the speed of light. When the charge reaches this point, it will be subject to a sudden instantaneous acceleration. and you can select here the value of this acceleration. If we move this cursor here, we will have larger or lower acceleration. And this is just the time scale here. So now I move along the path, and you see that those are just the radial field lines we had before. Those are just the radial Coulomb lines. And nothing changed here because this is uniform motion. Now, we reach the charge. What happens here? There's a sudden acceleration. So now the charge will be generating a new set of radial lines, but they are no longer aligned with the previous one. So the field lines will reach this point, and it will have to continue on this. That means that they will have to bend in this direction. And this is just the term for which we have written the expressions before. Those are the radial, the Coulomb term, and the delay term, and this is the radial field. And you see that it's in some way transversal, it's perpendicular to the radial component. And if we keep moving, you see that this just keep increasing because just this wavefront is just going far away. We may go back on time and just increase the change in velocity, the acceleration. And you will see that the effect is exactly the same. Reaching this point, we'll have this circle that will expand, and this is just the kind of fields for which we have written the expressions before. I invite you to visit this website and have a look through their demonstrations. They are quite interesting in general. Here you have the address. You may just go to this wolfram.com demonstrations, and you can choose very different ones. The one I have shown you is just the radiation pulse from an accelerated charge.